This technique will help you to navigate through the different quantities in electric fields or gravitational fields. We're going to do that in gravitational fields as well. So it's called Fwev, and I'm going to tell you what Fwev is. So I start by doing a big line here, and I'm going to write Fwev. Now, a few years back we did that because it just helps us to understand what they are. So obviously this is force, so an electric force or gravitational force, an electric field strength, work done, potential. So if you want to know what the units are, well, the units are Newton. E, electric field strength is Newton per Coulomb, or volts per meter. Yeah? And also work done is joules. This is potential. But here's the best part, is how you navigate from one to the other. So the technique was, all we do is have a bit of fun. Q, Q, R, R, Q, Q, R, R, Q, Q, R, R, Q, Q, R, R. Now notice that I haven't put 1 over pi epsilon naught, right? Because that's a constant. I could leave it as K. I'm not interested in that. But look what we're going to do now. Force, product of the charges over inverse square law. What's electric field strength? Force per unit charge. So you cross a Q. Work done. Force times distance. Force multiplied by distance, you cross out an R. And potential is, you cross 1 each. Now you'll be thinking, well, I get that from the equation. But here's what happens next. Because if you want to go this way, if you want to go this way, what do? You're multiplied by Q. And what does that show to you? That shows to you that W is equal to Q times V. Brings the equation. Likewise at the top, we do the same. If you want to go there, F is equal to what? QE. Okay? Next is what comes up a lot in the exam. Is how do we now go from the bottom to the top? And for that, if you differentiate Q over R, isn't it QR minus 1? If I was to differentiate these with respect to R, guess what it becomes? There's a minus that comes from the front. The Q stays. R minus 1 becomes R minus 2. Guess what it becomes? Everyone okay with this? So it means if you differentiate this, you get that. If you differentiate this, you get that. So E is dV by dr, and there's a little minus there. But for electric field, that minus will come in depending on the charge. And guess what? F is dW by dr. And you know it from GCSE because work done is what? Force times distance. Okay, we've done all of that. And then the next part where students struggle is this. The graphs. The graphs. Potential tends to be what? Negative. So if they give you a graph and they say to you that's potential, dV by dr looks like that. If you differentiate that, guess what this graph would look like? It's the gradient of this one. What does it become? No, because if you differentiate 1 over r, what do you get? It actually positive, but it curves a bit better. And that's what? Electric field strength. As you go further, the same principle goes on the other side. So I'm going to ask you questions, and I'm going to say to you, oh, you're going to say to me, sir, potential energy, how is that related to potential? Sir, work done, how is it related to force? I'm going to say to you, you do Fwev. You do Fwev. From potential, how do you get to work done? Multiplied by charge. From here to here, gradient. If you get a graph of this one, to go to the top, dW by dr. You guys are the further maths class, you should know. dW by dr is the differentiation, is the gradient. So next lesson, I'm going to go over this. And I'm going to give you a blank board. And I'm going to say to you, I want you to do Fwev the way I've done it. Right? Okay, thank you.